Hello everyone and welcome back to Happy Little Diodes. Today we're going to be sprucing up an issue 2 Spectrum 48K that my old colleague dug out of his attic. This guy really knew his stuff and really got some good use out of this thing, as was evident by the box of peripherals, breadboards, hand-drawn schematics and spare chips that came with it, not to mention the stacks of bucks. In part 2 of this video we'll explore the peripherals and bucks. Today we're just going to get the machine repaired and future-proofed. A first look shows that the faceplate is a bit tired, a sign of tough love and heavy use. The case is in great nick though, and the edge connector is pristine because it's been stored with an interface 2 attached. Not so bad. I knew that it booted, but plugging it in gave the same issue as we saw in the previous repair, this flickering messed up text. It should be easily fixed by swapping out the ULA. Again, these are hard to come by, so it's best to use a modern replacement such as the VLA82. It slots straight into the socket and it just works. Easy. Unfortunately, as is common with issue 2s, the picture wasn't quite right, either blue or yellow. You can try to sort this out by twiddling VR1 and VR2 shown here, but I just couldn't get it perfect, so we'll come back to it once the capacitors are replaced and do it properly. Let's have a tour of the board. We can see the giveaway transistor mod over the Z80 CPU. They came from the factory like this. IC23 is standing proud of the board. It looks like it was manufactured like that. I'm not going to change it, as it won't make any difference. IC24 is in a socket. I guess it was replaced at some point. More interestingly, IC26 has a pin disconnected from the socket and shorted to 5 volts with a white wire. This is unusual, but it's not the first time I've seen it. Now seems like a good opportunity to really figure out what's going on with this mod. I hope you're ready for a bit of detail. If you're not, you can either skip ahead about 7 or 8 minutes, or enjoy some clips of the cats. If you know a lot about spectrums, then I can just say that this mod's been done because OKI chips are fitted to upper memory, which use column address strobe to select their operational half, instead of row address strobe like the Texas Instrument chips. On boards before issue 3, there wasn't an easy link to solder to allow for this, hence the mod. For anyone else interested, let's start from the bottom. Right, that's the cat sorted. So, how does RAM work? A chip of RAM, called random access memory, can store data in the form of zeros and ones. We can store any binary data we want in there. By the way, each 0 or 1 is called a bit, which is short for binary digit. An 8 binary digits stringed together is called a byte. RAM chips can be arranged in a number of different ways. On older machines, you might find that the bits are grouped into 4s. Each group of 4 is called a word, and each word has its own address, shown in green. In this example, if we asked the chip to tell us what's stored at address 5, it would return 0110. Our Spectrum 48K is a Spectrum 16K with an extra 32 kilobytes of memory. This works out to 32,768 extra bytes of available storage. So for us, the extra memory looks more like this. Each address stores 8 bits or 1 byte of information. However, the chips used in the upper memory only store 1 bit of data per address, like this. So in order to achieve 32 kilobytes, we have to have 8 chips in a row, like this. When we ask to read from, or write to, a particular address, the same address is sent to all 8 chips at the same time, so it's neater to draw it like this. If we asked for the contents of address 5 in this example, we would get 10111111. That's basically how the expansion RAM works, but we need to go further to understand this mod. You need to know that our example wouldn't be possible as I've shown it, because the memory chip only understands 1s and 0s. We can't ask it to read address 5. We have to convert 5 to binary, which is 101. You can see that we need 3 address bits, 1, 0 and 1, to ask it for the contents of address 5. In fact, to use address 32,767, we need to be able to give the address 1111, 1111, 1111, 111. That's 15 address bits. But it gets better. The chips used in the upper memory are actually 64K chips. This means they have 65,536 addressable locations, and that means we need one more bit to be able to address all of the locations, like this. That's 16 address bits. I've highlighted the first one red because it's particularly interesting to us. We're going to call it the red bit. You might have noticed that the first half of the memory, the first 32,768 addresses, start with a 0, and the second half of the memory, that's the second 32,768 addresses, start with a 1. Remember that. So, this is how we store and address 64 kilobytes of information. Great. Now let's have a look at the actual memory chips. You can count that they each have 16 pins. So let's figure it out. One of those has to be for power. One of those must be for ground. One for the data that we're trying to write, and one for the data that we're trying to read from the chip. We also need one pin to tell the chip if we're reading from it or writing to it. That only leaves 11 pins. So how are we going to get our 16 address bits in? The answer's quite clever. The chip gives us 8 address lines, A0 through to A7. We have to set up the first 8 bits of our address on these 8 pins, and then latch them in with a latch. We'll call it latch 1. We then set up the remaining 8 bits of our address, and latch them in using latch 2. The memory now knows the 16-bit address that we're interested in, and can do our bidding. There's even a free pin, very efficient. By the way, latch 1 and latch 2 are called RAS and CAS. That means row address strobe and column address strobe. I mentioned earlier that only half of the memory locations in these chips actually works. The question is which half. This is printed on the chip. You will either see L or H, meaning lower or higher. On this machine, you can see that our chips are M3732H. So we know only the higher half of our memory chips works. And what does that mean for our addressing? It means all of our addresses must start with a 1. Now, let's consider our chip with the bent leg. Remember that we have to set up the first 8 bits of our address first, latch them in, and then set up the remaining 8 bits. Well, this chip, along with IC25, takes a 15-bit address from the CPU, plus the red bit, which in our case must be a 1, because we have H chips, and splits these 16-bit addresses into 2 sets of 8 bits ready to be latched into memory with RAS and then CAS. The first 8 bits are set up, RAS latches them into memory and tells IC25 and IC26 to set up the remaining 8 bits, which are then latched in with CAS. The key point here is that the red bit is latched in when RAS is set. The usual way to force a red bit to a 1 is to solder a wire between these 2 joints on the PCB, highlighted green. This forces the red address bit to 5 volts, which is the same as a 1, and means we only use the working upper half of our memory chips. Incidentally, if you have an L on your chips, you have to solder the middle joint to the bottom joint. This link goes directly to pin 10 on IC26. But on this machine, the link hasn't been made at all, which would imply a floating pin on pin 10, which would be bad. However, turning the board over, we can see that pin 10 has been shorted to the joint where pin 11 should be connected. This means pin 10 is receiving what pin 11 should be receiving if it hadn't been bent up out of the socket. Pin 11 has been joined directly to a 5V supply with this white wire. So here's what we have. Pins 10 and 11 have essentially been swapped on our board. As it happens, pins 10 and 11 correspond to these bits highlighted at the bottom. Pin 10 carries the important red bit, and pin 11 carries an address bit from the CPU. This means that this is what's actually happening on our machine. Our red bit is getting passed through on CAS instead of RAS. The reason for this is simple. This machine has been fitted with OKI chips, which select their operational half on CAS instead of RAS. That's why this mod has been made. On later issue Spectrums, a second link was provided on the PCB, which simplified this a lot. It's even labelled LNH and TI for Texas Instruments and OKI for chips like ours. Moving on. This board has had the DC-DC modification. This is a service mod that adds a capacitor and swaps a resistor in the power circuit. This helps to prevent transistors from exploding, which looks like it's already happened on this board. Anyway, let's change all the capacitors. I'm not setting a great example here. It's better to remove one capacitor at a time, replace it, and check that it still works. That way if you have any issues you can trace it back quite easily. I had some trouble with clearing the joints after removing the caps. It took a really long time, and when this happens, and it will, just stop when you start to feel frustrated. Come back with more solder wick and try again. Add solder to remove stubborn solder and take your time. I still need a lot of practice with this, but I'm getting better all the time. A quick note for the two capacitors that are right next to the heatsink. These are going to get hot, so recap kits often come with caps rated to a higher temperature. The only issue is that axial capacitors are hard to come by, so you'll have to use radial capacitors and bend the positive leg over itself to make it fit. Also, beware of a printing error on issue 2 boards. C46 has its positive leg on the left, not the right as the printing would suggest. The DC-DC mod uses an additional 4.7 microfarad capacitor soldered between R48 and the positive leg of C34. I decided to replace that too for good measure. Oh, and see that blue resistor that I've put in? Ignore it. I'll explain later. At this point I plugged it in and got garbage on the screen. I'd seriously broken something. Luckily I found a rogue solder blob that was shorting some tracks together. Remember, always clean up your solder splashes. I was lucky that nothing popped. A quick go with a wick and everything was okay. Unfortunately the annoying yellow band was still there. Otherwise the picture looked good, but not as good as it would be after a composite video mod. So let's do that. Before going any further, the keyboard membrane had to be replaced. As usual, it had totally disintegrated. It's a bit messier with issue 2's because the front panel is glued on, a job for the heat gun. I used mine on the lowest setting, and it worked really well. You can see here how old and yellow the glue is. I'm gonna need to remove it all before replacing the faceplate. Underneath, we have the keyboard and the old membrane. You can see that the tracks to the board are completely gone. I used surgical spirit to clear up the glue. It went fairly easily on the case, but took a lot more effort on the metal faceplate. The spirit also made short work of this yellow mark on the Sinclair logo. The new membrane slotted in easily and fits perfect. I popped the keyboard back on, but didn't glue the faceplate on just yet, as I wanted to check that the new membrane worked. No problems there, except the annoying yellow band. I glued the faceplate back on, and to be honest it wasn't my finest hour. I'd worsened the condition of the faceplate in rubbing off the old glue, and got a bit of excess glue on it, which removes the paint if I try to sort it out. But this is a repair, not a restoration, and I like the rugged look. It's like an old Stratocaster. This command tells me how much working memory we have. We're looking for 64K. Result. Time to load a game. Well, the yellow stripe has turned into a bit of a blue apocalypse, and Manic Miner would probably rather I turned the machine off. So I did, and when I did, I noticed the spectrum was incredibly hot. First protocol was a power circuit. We had 9 volts in and 5 volts out of the regulator, 5 volts and minus 5 volts on the supply rails, and 17.7 volts on the 12 volt rail. That's why I unplugged it pretty bloody quickly. Unfortunately, while I was testing those voltages, the ULA died a death. Maybe I shorted the 17 volts with a probe. I'm not sure, but it's definitely knackered. Shame. Going back to the problem, remember that blue resistor I told you to ignore? Well, that's the 270 ohm resistor in this schematic, only I'd fitted it at R58. Oops. Quickly sorted that, and the voltages were back to normal. Remember that annoying yellow stripe? The best way to attack this is by adjusting the two variable resistors VR1 and VR2 until the picture looks good. The timing adjuster TC2 above also has an effect. You can often get this right just by twiddling, but I couldn't, so I finally got to use my nifty little oscilloscope. If you probe the composite video output and adjust VR1 and VR2 until there's very little noise, you should have a good picture. There we go, miles better. Only one thing for it. Let's have a game of Frogger. Turns out Frogger was absolutely nails in 1992.